So I'm working with my whiteboard today. And what I'm going to do is I have a series of pages and I'm going to work through a couple of examples and talk my thinking through as I go through. So this is about scientific notation. So I have 4 numbers here that I'm going to put in scientific notation. Remember that we use scientific notation in science because we want to write extremely large numbers and extremely small numbers in a very efficient way, a very compact and efficient way. All right, so number 1 right here. My answers are going to be written in blue. I might have to erase a few times. This is not a very sensitive stylus, and I am just now getting used to how to use a whiteboard instead of actually writing physically on a piece of paper or on a whiteboard in the classroom or a chalkboard. So bear with me with that one. Okay, so number 1, we have 300,000. The first thing that you want to do is ask yourself, is this number larger than 1, or is it a number that's between 0 and 1? So is it a very, very small decimal, or is it a very large number? This is a very large number. And then what you want to do is do a series of hops to figure out how many powers of 10 you're going to need. Because if you multiply something by 10, you just add a 0 to the end. So the easy way to do this is I'm going to put the decimal place right there, and then I'm going to count how many spaces I need to move it until I have 3.0. All right, so let's count spaces. 1, 2, 3, 4, 5. So that's 1, 2, 3, 4, 5 spaces. And that tells me that that would be a 3 multiplied by 10 to the 5th power. 10 times 10 raised to the 5th power. So this answer should be 3 with 5 zeros after it. I'm sorry about the dot right there. And that's how you'd write 300,000 in scientific notation. Not that bad. 300,000 is not that hard to write, but this next number is considerably larger. Here we have 149,600,000. If you're trying to write that over and over and over again, you might get tired of counting all the zeros and making sure you get everything right. So scientific notation is going to be a little bit more useful here. And again, we're going to do the same method. So I want to put the main number in decimal notation. I'm going to keep all the digits, 4, 9, 6. So I have 1.496. So I want to move the decimal place between the 1 and the 4. So I have a number in the ones place right here. So that would be 1, 2, 3, 4, 5, 6, 7, 8 hops. So that one was the 8th hop. So this would be times 10 to the 8th. And times 10 to the 8th, that would tell me to move this decimal place over 1, 2, 3, 4, 5, 6, 7, 8 times. And I would be back to this expression over here of 149,000 or 149,600,000. A easier way to write it right here. Okay, now we're going to go to an example where we have a very, very small decimal number. It's still a positive number, but it's between 0 and 1, a very, 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 very small fraction. 0.000047 equals, and we're going to start this the same way. Take the number that you're aiming. You want to always express it as the ones place, a decimal point, and then whatever came after that. So 4.7. So I know I want to put my decimal point eventually right there between the 4 and the 7. And I'm going to count how many hops it takes to get over there. 1, 2, 3, 4, 5 hops. So it's going to be times 10, but this time it's going to be to the minus 5. And just a reminder over here, 10 to the minus 5. Let me go ahead and write that a little bit more clearly for you. 10 to the minus 5 equals 1 over 10 to the 5. So it is a number that's a very, very small number, 1 divided by 100,000. So 1/100,000th. And that's how you'd write the small number in scientific notation. Here we use the minus 5 because I counted hopping this over 5 times, and the number is a very, very, very small number This is a little bit greater than 0. It's between 0 and 1. Okay, and what do we do if we have a negative sign out front? Well, a negative number is still a negative number. So in this case, going to start, I still keep my minus sign, so it's minus 1's place, and then what would come after it? 8.5, so I want my decimal point to be right there. How many hops do I have to take there to get there? 1, 2, 3. So times 10, but I was moving the decimal place over to the right. This is a very small number right here. So it would be to the minus 3. Hopefully that's a review for a lot of you. Let's go ahead and move on to what I'm sure most of you are interested in. And that's really with the metric system. So instead of how I did this before, I'm going to write out every prefix, its symbol, and what power of 10 it relates to, because the metric system, and really just this prefix system more than the metric system, is really relying on powers of 10. The metric system is based on powers of 10, so it lends itself nicely to the metric system. So I'm going to start large and work my way small. Let's go ahead and start with the prefix, the large prefix, giga. And the way I'll do this is I'm going to write the prefix, and then I'm going to write what the symbol is, capital G, and then I'm going to write what power of 10 it is. 10 to the 9th equals 1 billion. So I can write it in a scientific notation. So anytime you see giga, you're talking about 10 to the 9th of something, 1 billion of something. A very large amount of that thing, whatever it is that we're measuring, whether it's meters or hertz or seconds. Now we have another large one, mega. And for this, yes, it's a capital M, and capitalization is important. And this one is 10 to the 6th equals 1 million of something. Now let's go to the next one. Kilo, a lowercase k, 10 to the 3rd. Notice that each one of these, 10 to the 3rd, so we have 3, 6, 9, always going by a factor of 1,000 between these. And this is 1,000. Not too bad. And it's really, this is those things where you just have to start associating the prefix with a symbol and just get used to seeing it. It takes practice. There's no other way around it. If this is an unfamiliar system to you, you're going to have to sit down and play with it a whole lot, come up with mnemonics to help you remember. However you can learn this, it's one of those things that once you learn, it'll be stuck in your head forever, and then you can operate with the rest of the world with a metric system. Okay, so let's now go to the smaller ones. And I'm going to come back to centi. I want to go to milli first, because we're going to see a pattern here. So prefix, milli, lowercase m is the symbol, and this is 10 to the minus 3 equals 1 over 1,000. So this is 1,000th of something. Okay, the next one is micro. Now this symbol is a little bit different. It's the Greek letter mu, which looks like that. It looks like a squiggly M with a big long tail. I always like to think about it. I'm going to write it again. It looks like a U that I'm going to switch into an M. So MU, the Greek letter mu. And that stands for micro. And that's 10. Notice that these were all powers. So it was 10 to the 9th, 6th, 3rd. There's a difference in the exponent of 3. This is 10 to the minus 6. A nice little pattern that we have going on. So this is 1 over 1, 2, 3, 4, 5, 6, 1 million. So this is 1 millionth. Really, 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 really small. And then we have nano. Prefix or the symbol is just a lowercase n. And it's 10 to the minus, 3, 6, 9. And I'm not going to write out the big fraction. I'll just write this is 1 billionth. So I wanted to write those ones out before I added in the centi one. So you can see that for the majority of the ones that we're going to use in this class, the prefixes and the symbols, we have this nice pattern where it goes 9, 6, 3, and then it'd be 10 to the 0 is 1 for the base unit, and then minus 3, minus 6, minus 9. Each one of these is different by a factor of 1,000. So it's just adding 3 zeros or adding 3 more zeros between the decimal point and the number if we're in the really, really small realm. And now we can add the oddball that we use because it's just a useful one. Centi, which is a lowercase c, and this one is 10 to the minus 2. One hundredth. Okay, so hopefully a nice, slow me writing them all out will help you. These are things, just write them down, get used to using them. This translation right here, I wrote them in the scientific notation over here, because this is what I'm going to use to show you a set method of how you can convert between units. There are a number of ways. You should just come up with the method that's most comfortable for you. I am usually against just the strict teaching of algorithms because that tells you to follow a recipe rather than understand what's going on. But in following a recipe, you can actually learn what's going on. So I'm going to show you a method to convert. Sometimes it's going to make the problem more difficult to do than just reasoning it out, but it gives you a standard set way to do this over and over and over and over again. So in this question number 1, we're going to take 23 kilometers and we're going to convert it to meters. And notice that kilo K is 10 to the third of something. Oh, that's not very clear. So the first step I want you to do is convert to the base unit. And the easiest way to do that is we want to go from the base unit for distance is the meter. So we want to go from kilometers to meters in this case. So we're just only going to have to do step 1 here. And just go ahead, what does this K mean? And actually just write it out. It means 10 to the third. So what do I have now? I have 23 times 10 to the third. Let's write that in proper scientific notation. So I'd have to move this decimal point over 1. So it'd be 2.3 times 10 to the 1 times 10 to the third, because we still have the times 10 to the third. 1 plus 3 is 4. 2.3 times 10 to the fourth meters. Let's write that out all the way. So that would be 2, and now I'm going to have 4 places after the decimal point. 1, 2, 3, 4, 23,000 meters. Now I want to start with a simple example like this to hopefully reinforce that you can logic your way to a lot of these answers, because 23 kilometers, let me say that out loud, replacing what the kilo means. 23,000 meters. Oh, that got me directly to my answer. 23,000 meters. Not that bad. And that gives you, so that was just step one. We went directly to the base unit. And you can keep it in scientific notation if you want, or you can put it all the way out in this long form. And once you get used to it, you might just want to go ahead and skip some steps here and go, oh, 23 kilometers, 23,000 meters is 23,000 meters. All right, so now let's do number two. Let's follow the method, and then we'll talk a little bit about how you can logic your way through it, and we'll exploit the fact that there is a factor of 1,000 between giga and mega. So here we have 46 gigahertz, and I want this in megahertz. Let's convert the gigahertz just to hertz first. And the easiest way to do that is, oh, I know that giga is 10 to the 9th hertz. So I have 46 billion hertz. So now I have 46 times 10 to the 9 hertz. And now that I have the base unit, I can convert that to megahertz. And the way I'm going to do this is what's typically called the train tracks method of unit conversion. So what I'm going to do is I'm going to draw everything as a series of fractions. But I'm going to make it look like train tracks, where that would be my my actual railroad, and there's my cross part. So what I'm going to do is I want my answer in megahertz. So my goal is going to go on the top. But I'm using this unit right here. I have information in hertz. So now I want to put something here in this region right here that's equal to 1. Let's see if I can just go ahead and erase that. I don't want you to get too confused. You don't have to draw circles. I just wanted to highlight that for you. So now I want to know how many hertz are in a megahertz. Well, mega is 10 to the 6th, right? So there's 10 to the 6th. There's 1 million hertz in 1 megahertz. And now you multiply across the top. You divide by the stuff on the bottom. So I would have 46 times 10 to the 9th divided by 10 to the 6th. If you remember your rules of exponents, I can cancel that out. And that means that this would get reduced by 6. So 9 minus 6 is 3 equals 46 times 10 to the 3rd megahertz, because these units would cancel. Now let's write that in proper scientific notation. 4.6 times 10 to the, move this over 1. So add 1 to the 3, 10 to the 4th megahertz. Which you could just write, and I'm going to squeeze this in. That would be 46,000 megahertz. Sorry, I got squeezed in a little bit right there. I'm still learning how to manage my space on these whiteboards. So that would be, all of these are good answers. Both of those right there. This is even a pretty good answer if you're communicating. You can say, oh, I have 46 times 10 to the 3rd megahertz. Now, let's take a look at that. 46 times 10 to the 3rd. What is 10 to the 3rd larger than mega? Giga. I know that mega over here is 10 to the 6th. So there is a factor of 1,000 between these. This is 1,000 times bigger than that. So if giga is 1,000 times bigger than mega, and I have 46 giga something, that means I would have 46,000 mega something. And that's another way you could logic your way through it. Once you get used to the prefixes, I can look at 46 gigahertz and megahertz and convert that directly to megahertz, because I know giga is 1,000 times bigger than mega. So I can just do 46,000 megahertz. And I know that equals 46 gigahertz. Probably should have used a different color for that. I apologize. Hopefully you were following along to what I was doing. If not, make sure your audio is on, which it doesn't do any good to tell that to you. All right, so let's continue going on with this. Here we're going from 550 nanometers to micrometers. Again, convert to the base unit. Nano is 10 to the minus 9. So now I have 550 times 10 to the minus 9 meters. Just wrote it out in a space unit. Step 1 accomplished. What is step 2? Use the train track methods to convert to the desired unit. Okay, I am given information in, I want to take this meters and I want to convert it to micrometers. I know the meters are bigger, so I want to ask myself how many micrometers, microns as we call that in the business, are in 1 meter. Well, if micro means 1 millionth, then I need 1 million of these things, to 1 million micrometers to equal 1 meter. Multiply across the top, divide by what's on the bottom. So this would be 550 times 10 to the minus 9 times 10 to the 6th. Oops, that's not erase. I was erasing my other program. And what does that equal? What's 10 to the minus 9 times 10 to the 6 is 10 to the minus 3. Minus 9 plus 6 is minus 3. 550 times 10 to the minus 3. That's 1,000th of something. So I'd have to hop this decimal place over 1, 2, 3 spots. So we get our answer equals 0.55. And I'm going to leave off that trailing 0. Micrometers, 0.55 microns. Hopefully that was easy to follow. Now let's go ahead. This is 10 to the minus 9. Micro is, and now I will use a different color, 10 to the minus 6. So we have micro is 1,000 times bigger than nano. So if micro is 1,000 times bigger than nano, then 1,000 nanometers would equal 1 micrometer. So if I had 550 nanometers, draw my train tracks, and I'm going to go from nano directly to micro, and I know I have 1,000 of these and 1 of those. So that would just directly get me to 550 divided by 1,000. Cancel out my nanometers. That would be in micrometers equals 0.55 micrometers. So again, the standard method, and then we're using a little bit more advanced knowledge of, I really know my prefixes, so I can skip a couple of steps. And that green solution was a lot quicker and more rapid. And I see this problem, and I see 550 nanometers to micrometers, and I'm like, oh yeah, there's 1,000 nanometers and 1 micron. I'll just divide 550 by 1,000, 0.55 microns. So the more you work with it, the better and easier it gets. All right, so continuing on, 71 centikelvin to nanokelvin. Get rid of the centi. Let's go to our base unit, our Kelvin, our measure of temperature. Centi is 10 to the minus 2. So I'm going to rewrite this. 71 times 10 to the minus 2 Kelvin. I'm going to use my train tracks method. Now I want to go from Kelvin, because I want to cancel those units out, to nanokelvin. Okay, what does nano mean? Nano is 10 to the minus 9. So it's 10 to the minus 9, which would mean that I need 10 to the 9th of them. 1 billion nanokelvin is 1 Kelvin. Now I can cross out the Kelvin, multiply across the top, and you get 71 times 10 to the minus 2 times 10 to the 9. Minus 2 plus 9 is plus 7 equals 71 times 10 to the 7th nanokelvin. And with this one, you could leave it like this, but let's put it in proper scientific notation. 7.1. Move this over 1, so it would not be 10 to the 7, it would be 10 to the 8th nanokelvin. 710 million nanokelvin. And with this one, since these 10 to the minus 2 and 10 to the minus 9 are so different, you could go ahead and do a process up here where you could logic your way a little bit to it. You can see that there's a difference of minus 2 to minus 7. That's a difference of 7, 10 to the 7. So this is 7 times bigger. So I would need 71 times 10 to the 7th to convert between centikelvin to nanokelvin. I know I just said that one out loud, but in more complicated ones like this, and I'm running out of space a little bit, I wanted to just go ahead and give you this set method so you can get to your answer without any problems at all. And let's just do one last one to make sure that we really get this. 60,000 milli, notice that's a lowercase m, watts to kilowatts. All right, let's go to our base unit. And the way that I've been doing it is mark out the milli and write what that is. That's 10 to the minus 3. So now I have 60,000 times 10 to the minus 3 watts. And I want to convert that. So draw my train tracks. I'm going to go from watts to kilowatts. So I need to ask myself, kilowatts is bigger than watts. So how many watts are in 1 kilowatt? 1,000 watts equals 1 kilowatt. Cancel these. I have 3 zeros here, so I'll cancel those and cancel 3 zeros here. So this would give me 60 times 10 to the minus 3 kilowatts. And now I want to get rid of that minus 3, so I'm going to take this decimal place. I'm going to hop it over 1, 2, 3 spots. So this would equal 0.06 kilowatts, if you want to put it that way. Which also equals 6.0 times 10 to the, oh, I'm out of room. Let me go ahead and put that down below. Equals 6.0 times 10 to the minus 2 kilowatts in proper scientific notation. And hopefully seeing these extra 5 examples and with a set method is really helping you out. I do want to show you one last example just to show you the power of the train tracks methods. I'm going to do a multi-step conversion. That was one of the things people had asked about, is how you do multi-step conversions. We were technically just doing 2-step conversions. We'd first go to the base unit, and then from the base unit, we'd apply our knowledge of the prefixes to go to our desired unit. But in this one, let's just go ahead and do a multi-step thing just so you can see how conversions work in general to sort of reinforce that there's a commonality that's going on here. So let's go ahead and fix the typo that I had preset by adding a question mark. So the question is, how many seconds are in 1 year? And I'm going to use the train track method And then we'll go ahead and I'll reinforce some of this prefix business at the end of this question. Again, notice that it says this is beyond quiz and exam material. You don't have to do this for quizzes or exams. It is a good skill to have, however, and it really reinforces what I've been talking about for the last while. All right, so I'm going to start with what I'm given. I have 1 year. Eventually, I want to take that down to seconds, but I'm going to take this step by step. So I'm going to start drawing my train track. And I want to go from year. Well, I know that 1 year is 365.25 days. Okay, days is not seconds. I still got to keep on going. So let's just draw another part of the train tracks. Now I want to go from 1 day. Well, there are 24 hours in 1 day, not to second. Now I want to go from hour. So in 1 hour, there are 60 minutes. Almost a second, because I know in 1 minute, there are 60 seconds. What would that equal? You'd multiply across the top, divide by the bottom. So I'm going to break out my trusty calculator here. Always good to have one of these. So I would have 1 times 365.25 times 24 times 60 times 60, all divided by 1. Go through, make sure all my units cancel out. So I'm left with seconds. What does this equal? 3.15, and I'll round to the third decimal place. 156 times 10 to the 7th seconds. Now I'm going to show you how you might want to say, oh, I don't want this in seconds. Let's put it in, let's use one of the prefixes. So 3.156 times 10 to the 7th seconds would be the same as 31.56. All I did, if I move this decimal place to the right one, then I would make this 7 one less, so it would be 31.56 times 10 to the 6th seconds. What is my 10 to the 6th? 10 to the 6th is mega, so this would equal 31.56 megaseconds is 1 year. All right, I know this was a little bit of a long video. Hopefully you have digested it in smaller chunks. I'm going to go ahead and end things here. Thank you for tuning in.